So we learned a confidence interval for the population mean mu, and we also learned how to do a hypothesis test for the population mean mu. And now we're going to talk about the assumptions that we actually should have checked before we made that inference in order for the t-based inference that we use to be valid. And what do we mean by t-based inference? We mean that we made inference on a population parameter based upon using the t-distribution for our test statistic. So we have two main assumptions that need checked. The first one is that the observations have to be independent of one another. Now we'll usually just check to make sure that the data is from a random sample from a large population. So if it's mentioned somewhere, we're going to assume that this is good, and if it's a random sample, then the observations are probably independent of one another. There are other ways that dependence can sneak in, so we've listed this a second time, that we need to verify that the observations are in fact independent of each other. Think about if you're doing a study on weight and you get identical twins in your sample. The weights of the two identical twins would not be independent of one another. Knowledge of one would give you a little bit of information about where you think the other one would be. So anyway, the observations in a sample have to be independent of one another. The second assumption, the one we'll be doing some work to do some checking on this semester, is that the sampling distribution of the sample mean needs to come from a normal distribution. Now remember the boxed set of theorems in Chapter 5 that we learned that the sample mean does have a normal distribution if the original observations came from a normal distribution, or as long as your sample size is large enough, even if those original observations didn't come from a normal distribution, the central limit theorem will kick in and get us that the sample mean has a normal distribution. So if you have a small sample size, the central limit theorem isn't going to work for you to give you that the sample mean has a normal distribution. So if the sample size is small, the population distribution needs to look like it came from approximately a normal distribution, a unimodal symmetric distribution. However, if your sample size is large, then your population need not be from a normal distribution because the central limit theorem can kick in for us. Now, we've brought this up several times, and at this point we need to talk about how small is small and how large is large. How big of a sample size do we need in order for that central limit theorem to kick in? We're going to talk about that in a second, but first we're going to define the word robust. So a statistical procedure is said to be robust if the results of the procedure are not very affected much when the conditions for validity are violated. So robust means strong, sort of. So we use the term robust for a statistical procedure if the results of the procedure don't get affected very much when those conditions for validity are violated. So now we're going to talk about the T procedures. And when we say the T procedures, we mean those based on the T distribution. Those are fairly robust to non-normality except in the case of outliers or strong skewness. Why is that? Well, think about your test statistic. Your test statistic is the sample mean minus the null hypothesized belief of what the true mean is, divided by the standard error, s over the square root of n. This has the sample mean and s in it, and both of those are extremely sensitive to outliers or extreme observations. So x bar and s are sensitive to extreme observations, and if those are sensitive to extreme observations, so will the calculation of the test statistic. So we need some guidelines for how big of a sample size we need for the central limit theorem to kick in so that our sample mean, we can hope that it has a normal distribution. So we already sort of mentioned that the further away your original distribution is from normal, the bigger the sample size needs to be to correct for that, so that the central limit theorem will tell us that the sample mean has a normal distribution. And we also need to consider whether there are extreme observations and outliers in our distribution. So we're going to use the following loose guidelines as just sort of a rule of thumb to go by when we're making those decisions. So, if your sample size is less than 15, say, so if n is less than 15, we're going to consider that to be a small sample size. And in that case, we don't know that our central limit theorem is going to kick in. So, if n is less than 15, the observations should have come from approximately a normal distribution, a unimodal symmetric distribution. Now, how are we going to tell with a small sample size whether it looks like the observations might have come from a normal distribution? Well, we can't make a histogram out of less than 15 observations. It's not going to look very good. How did we check for normality of observations to look at whether the observations look like they came from a normal distribution? We looked at a QQ plot. So, if your sample size is less than 15, your QQ plot needs to look fairly linear. It needs to look pretty good. If your sample size is bigger than or equal to 15, this is going to be a moderate sample size. So if it's bigger than or equal to 15, then the central limit theorem is probably going to kick in. It's probably going to be okay to proceed with t-based inference as long as you don't have strong skewness or outliers. So if n is bigger than or equal to 15, it's okay to proceed with t-based inference as long as there is not strong skewness or outliers. And again, look at your QQ plot to see if it looks like there's evidence of strong skewness or outliers. And if n is bigger than 40, we're going to say that's a large enough sample size to correct for any kind of skewness or outliers. It is usually okay to proceed with t-based inference. The central limit theorem is usually going to work for you as long as your sample size is bigger than 40.